RF front-end overload or IF and IDC overload and safe and proper measurements using a spectrum analyzer. It is important to know what overloading means and what happens when you overload your spectrum analyzer, because it's a big difference between overloading and damage it, because overloading components happens way before you will damage your spectrum analyzer. And by overloading, I mean you will see false signals that is being generated by the active components that are currently experiencing overload inside of your spectrum analyzer. So the easiest way to explain this is first by start drawing out a typical block diagram. So I'll add a new layer here, and then I will draw first a typical low noise amplifier, and this can go into a digital step attenuator, and this can go into multiple filters, but I will only draw one. So this is the band pass filter. And this can go into an IQ-Demodulator, where we have our mixers. There, like, hello, 90 degrees, 0 degrees. And this can then go into some low pass filters. And this can then go into an ADC. Here we have the I, here are the Q, and then we have our antenna connected here. Then we can move this a little bit up here, make it a little bit smaller, and place it there. And then we can add our values. So this is a 20 dB gain amplifier. This is from 0 to 30 dB step attenuator. And this is from 60 to 6,000 megahertz band pass filter. Now, let us imagine a transmitter. Transmitter is here and it's transmitting some sort of signals. Let's say it's transmitting a minus 40 dBm signal. That signal will get had 20 dB of gain of that signal with minimum amount of noise from the noise amplifier. So now the output here will be minus 20, right? So you are giving it more dynamic range. So you're adding 20 dB of gain on your signal. So let us now imagine that it was minus 10 dBm. Easy math like that is plus 10 dBm. Are there a limit? Yes, of course. There are a limit to how much power that you can input your amplifier. So let's now imagine 0 dBm at input. The output will be 20 dBm. What will happen? Well, in the data sheet for your amplifiers, you usually have a value that is called the P1dB, the 1 dB compression point. Let me try and explain that to you here. You draw a line here to explain the power we add in, power in, and the power out. So back to our signal, right? We had signals in, we had signals in, signal out, right? This is plus, signal out. So this line here below is the signal that we add in. Sorry about the handwriting here. Minus 0. So the amplifier will add 20 dB of gain for any signal in the range that it supports. That for this particular amplifier, this is I think it's at 0.01 to 10 gigahertz. It will add 20 dB again, like a linear line. So this is linear. So we'll add whatever type of signal that we push in, or it receives, it will add 20 dB of gain. So 20 dB gain. Well, it comes to a point where it can't, when the amplifier doesn't have any more headroom. It will start to drop off, and now it is non-linear. But the imaginary gain line is here. When you input too much power and the gain starts to drop by 1 dB away from its original gain value, this is 1 dB, that is the P1dB that you will find in the datasheet for your amplifier. For this particular amplifier, that's like a different red. For this particular amplifier, it's different from 0 to 3 GHz and from 3 GHz to 8 and from 8 to 10. I will round it up. So from 0 to 10 GHz, that value is 18 to 21 dBm. That means if the output after gain from your amplifier reaches the value for compression, it will start to produce harmonics and intermodulated products, because you are now overloading your amplifier, right? So now it will start, when this happens, it will generate harmonics and intermodulation and like typical distortion, right? Whoop. And this hope you can read some of this, my bad text here. So now it will do that. So it's really important to safely operate the spectrometer, because the warning at the front end that says plus 25 dBm, for example, or in many cases plus 20 dBm, that's the hard limit. That's when you break it, right? You need to stay at least 20 dB away from this number, right? Because that's when you can break certain components in your spectrum analyzer. But before that happens, your LNA will go into compression if you add too much power. So the LNA can have a breakage point at plus 20 dBm, but it can start to go into compression at -5, -10 dBm. Then it can start to go into compression, and then it will start to produce harmonics and intermodulation in your spectrum analyzer, so your view gets completely distorted, right? So that is really, really important to know. So let me show you, for those who are not familiar with harmonics or intermodulated products, let me show you just quick what that looks like. So and add a new layer. So now let's first do harmonics. Harmonics is fairly simple. You have a signal, F1 here, this is the signal, 0 dBm at 100 megahertz. So here we have this signal, 100 megahertz, and then suddenly, because of the harmonics, you will get an additional signal at F2, and this is the 200 megahertz, and then you can get another one lower, F3, 300 megahertz, and F4, 400 megahertz. And this is the harmonics, right? Harmonics. So what is the easiest way for you to know if the harmonics is being generated inside your spectrum analyzer or from the outside? So let's say this value was -60, right? From 100 megahertz, you can use some typical free space path laws to know if you move further away, it will drop a couple of dBs, right? If you move further away from your antenna and all the harmonics disappear, then you know it's being generated from inside your spectrum analyzer, because if it was real and it was actually being broadcasted out in the air, harmonics wouldn't completely disappear when you start to move further away from your antenna, right? So that's one easy way to do it, or add some attenuation in front. So let's say I added 10 dB pad in the front, so my amplifier didn't go into compression and all the harmonics disappeared. Then you know it's from inside of your spectrum analyzer. The other thing that can happen is the intermodulation distortion. And I can show you what that looks like. First, I need to remove the harmonics view. Take that away. And then now we're going to look at intermodulation. So let us now imagine that we have two signals. Let's add a new one. Two signals at minus, no, not minus, but 101.5 megahertz and 102.0 megahertz. Each of them are strong enough so they will overload the amplifier. And then we draw this again. And then now we have these two signals. So these are the close by signals. And this is F1. And this is F2. And in modulation you get, like there, you get the sum. There, and the difference. Right, this is intermodulation, and there also higher order intermodulation, mixed together with the harmonics, and you will clearly see when things start to get overloaded. But this is intermodulation, right? So that was that. So now let's do a practice and see how this will look like in a spectrum view. So here we take a frequency here, DC to 10 gigahertz, and we have the signal here. Some spectrum, this is really high, this here, there, right? This is a spectrum that you're currently seeing now. And we have this really, really strong signal, minus 0 dBm, really, really strong signal spike here, right? And this can be at 20 megahertz, right? So this is on 20 megahertz. This wouldn't even be a signal that you can hear, because remember, your bandpass is from 60 megahertz to 6 gigahertz. So you probably wouldn't be able to see this signal at all. But remember, the LNA is from 0.01 to 10 gigahertz. It will add 20 dB of gain. 20 dB of gain to anything above that limit. Even the curve is probably a little bit lower. It will also add some gain of signals above and below. But this signal is on 20 megahertz. So when this enter, let's say this is plus 5 dBm on 20 megahertz, this will severely overload the amplifier, and you will not even be able to see it. But if you had such a strong signal, you will most likely, you would be really close with your antenna to some sort of transmitter. You will most likely will see it, right? So, but if you had to use some measurements either way, what can you do, right? So one of the first thing you can do, and something that I highly recommend, is by bypassing the LNA. You can bypass it and you come right into the step attenuator, and this is here where you set the reference level. So when you set the reference level to 0.0 dBm, you have the fullest amount of attenuation, and then you slowly go down, right, to -10 dBm. You move down, and if you start to see harmonics, or you start to see some sort of signals that just doesn't look right, you change it up again, right? So you use the reference level up and down, right? So I have a really good example of that I can show from a video that was shared by, I can paste it over here. Found a video from SignalHound, right? Let's see, then there. So here, you can see up here, let's see if I can draw here, this one maybe. Let's say there, you can see it's running in the IF overload. His reference level is -20 dBm, and you look closely at that spike there, that spike, right? So when if you see there, remove it. Now it's no overload anymore. Now we set the reference level to -10. -10. And where the spike? It's gone, right? So do this again. There it is. Gone. A typical type of overload. I also have some other quick examples here that I can show. This is a really complete overload of the complete ADC. I have some other examples here. Let's say there. There. Here is some intermodulated products from a really strong transmitter. So you see the copies of that signal. It's multiple of signals that have been copied. And here is the same little lump that you get on this right picture that you got in the other spectrum analyzer, right? Because the ADC or something got overloaded. So there's many type of examples. It's really easy to see. That's what I'm trying to say. It's really easy to see when things start to overload, right? Let's say, right? So one of the things that you can do to protect it, and then we remove this, and then we add something in the front. First, we can use an attenuator. Attenuator in the front. The attenuator will only, of course, attenuate the signal. So I can attenuate 20 dB. Right? The other things you can do is you can use filters. Filter is probably the most effective way to do it. If you really can't move any away from the transmitter. So you can just remove this first. And then we use something called a high pass filter. And this high pass filter, it will pass along signals that are high. So it will do this. The guaranteed value from here to some number up here. So that is a high pass filter. High pass. That will attenuate that signal. Let's say -10, -30, -60 dBm. So that will help attenuate that signal. So you can get high pass filters from 1 gigahertz, high pass from 2 gigahertz. A high pass filter I use is a 2 gigahertz high pass filter, and it attenuates signals below 1 gigahertz at around 65-70 dB. That's a good one. But I can still see the signals if it's plus dB, but it attenuate is not enough to protect it, right? So that is one way to do it. And another way you can do it, let's say the signal, this signal wasn't there, right? It was this was the strong signal, right? Let's imagine that. And then we can add something different here at the front end. And then we add a low pass filter. let's say now we only wanted to pass along this frequency. So that will mean like this. This there, for example, is that's a low pass filter. So that will attenuate that. So that is a good idea to protect from any strong signals entering your spectrum analyzer. And there's many other filters, but one filter that I often use, let's say I wanted to have band pass filter. Band pass filter can be like this. There. So let's say this is from 5 to 8 gigahertz, or 5 to 6 gigahertz, for example, because that makes more sense. So 5 to 6 gigahertz bandpass filter. So it covers all the 5 gigahertz Wi-Fi, right? So this can be a bandpass filter. So this will attenuate everything of this and everything of this, right? So whatever you are out there to measure, like use the proper filtering, and be careful not to overload any type of spectrum analyzer, right? A small little side note before we move on to some demos, that is there. This IQ-Demodulator also have a compression point, right? So this one that I found, 3 dB volts at 50 ohms, equal to 16 dBm, right? So that one can overload at 16 dBm. So be careful what kind of signals that you enter the LNA, and use the internal attenuator, right? Because there are some last thing here. There are the typical limiter, and the limiter helps by clamping down any strong signals so it will not enter a damaged components at the damage level. So a typical RF-Limter, that it can be from, let's say, a 10 watts to a 100 watt. You can handle that amount of energy. So let's say you get a signal at plus 12 dBm that enters your antenna. That will be clamped down to 10 dBm, and if you get any other strong signal, let's say a plus 15 dBm, that will also be clamped, let's say, down to 10.5 dBm. 20 dBm signal, now it's really starting to get a strong type of signals here, and that can be 10.8 dBm, right? So we'll only clamp down the signal to around 10 to 11 dBm, depending on the type of limiter that you have. That will protect your components from damage level, because the input of an LNA damage can be between plus 20 and plus 22. The input of an IQ-Demodulator can be also between plus 20 to 22 or 25 dBm, depending on the type of components that you have used. That's the damage level. And also a plus 10 dBm signal that comes out here. Let's say we do it like this instead. I'm writing it there. So let's say you push in plus 10 dBm. It will be clamped down to 10 dBm. So that would theoretically mean if the preamplifier could handle so strong signals that it didn't compress, that would be 10 dBm plus 20. That would mean theoretically, if you didn't use your internal attenuator, that the signal would be 30 dBm, right? And enter the IQ-Demodulator and possibly break it. But usually the low noise amplifier, these will go into compression, right? So compression, when they are introduced with a signal that is like plus 10 dBm. So the gain will drop, right? Gain drop. And you will see type of overloading behavior before anything gets damaged, right? But still, with your limiter, I would still recommend that you bypass the LNA, you didn't use it, and you set your reference level. Ref level. Start with a good amount of internal attenuation. Start with like minus 20 dBm, minus 10 dBm, whatever, before you're lowering it down. Right? A lot of numbers here. Let us go into Aaronia. That is the spectromizer I will use for this demo to show you a 5 GHz band pass filter and how I use reference level and what happens if you have burned your amplifier. So now onto the demos. So now onto demo with Aaronia spectromizer. So I will start it here with a reference level of minus 20 and my amplifier is turned off. So let's just show you first what this 20 dB of gain does if I add the amp. And I set the auto reference level. Right? So if you pause this picture now, what happened that I got around 20 dB of better receive sensitivity, right? The LNA a perfectly flat 20 dB of gain, right? Really flat, like perfect, right? So that is that. And I can also use the internal attenuation, right? So if I do this, set it lower, and then you see I'm raising, attenuating the signal more and more. So this is the reference level, the internal digital step attenuator that I'm tweaking here. So if I start by minus 20, for example, and I lower it down, lower it up, right? Then get better receive sensitivity, right? And if you've heard the stories that you can burn the amplifier in the hack RF, for example, you can do this with all kinds of amplifiers. If the signal is strong enough, or with static electricity, or something that severely overloaded an amplifier, it will break. So when that happens, it will act as an attenuator. On this one, that has happened. The preamp, most likely I did it when I played with some really strong signals and accidentally had a preamp turned on. I think it was me at least. And then the signal disappears. But I can just bypass it to a different amp or just disable it, right? So 1 amp minus 38 gives from my Wi-Fi and those levels around minus 100, absolutely perfect, right? And then what about this signal? This is a bandpass filter, right? This is a 5 GHz bandpass filter. So what do you think 2.4 looks like? And up to minus 104 dBm for Bluetooth. That is low, right? So if I look at this in a typical swept mission, and you will see quickly how well this bandpass filter behaves, right? Even with my amp turned on, and you don't see nothing, right? You see the Wi-Fi down here. I can set the reference level even higher. Let's set it to minus 30. And then the only thing I see is the Wi-Fi. So that is the power of a bandpass filter. So you can see, if you see the small spikes up here, that is my power meter indoors. That is strong. If I have my antenna placed a little bit differently, it will trigger up to minus 10 dBm, minus 5, and it will create harmonics all over the place. But with a proper bandpass, high pass, low pass, you will get all this kind of signals. So now LTE is completely dead. You can't see it because of the bandpass has attenuated all signals below 4.9 gigahertz with this particular bandpass. So I think that was a good enough demo. If you need to know more about Aaronia spectrum analyzer in general, you can visit my my Git book. Thank you.